Okay, right, week 5, everybody. We are looking at exponential functions and logarithms and power functions. And these questions this week are going to be a bit more challenging, I think, which is why I'm going to release these videos before the workshops. Let's just get stuck in. Question 5.1. Let me read the question. And this question is directly linked to the example that Andy gave in his lecture on Monday. So we're looking at a growth rate population equation, NT equals N naught times some growth factor R to the power T, and T is time in that case, right? So I'm asking, what is the number of rats at T equals 0 if I know this data, and there's some data here. And actually, I'm just going to write this out, and I'm going to show you what I actually mean by this constant factor R. Okay, so let's go and have a look. Okay, so I've got the data in front of me. I'm gonna take a bit of time with this. I'm gonna write it out. Okay, so let's rewrite that equation. N T is equal to N naught times R to the power T. Okay, and here's my data. I've got number of rats at time T. I've got time in months, and I've got the some factor R by which it increases every month. Okay, so R for each month. I'm going to calculate this, right? Let's do this. Right, 784, 1147, 1720, 2580. 3870, and of course I'm starting it in the 4th month. 4, 5, 6, 7, 8. Okay, so between each month to calculate that increase, I'm just gonna. Well, I don't know what it is because I won't know that for the first month, for month 4. Okay, that's my first value. But for the second, so between months 4 and 5, I can tell you the factor by which the number of rats is increased. If I take 1147 divided by 784, okay, if you do that on a calculator, you get roughly 1.5. Okay, so in that case, R is 1.5. Now, as it happens, the data I've given you, we can do that for all of this. So if I look at this value now, 1720 divided by this value the month before, that's again 1.5-ish. Then 2580 divided by 1720, surprise, 1.5. And then 3870 divided by 2580 is also 1.5. So what I was trying to get at with this data table is that you have this constant rate of increase from month to month of R, which is equal to 1.5. Okay, and I think, let's go back and have a look at the question. Yeah, so I've calculated R, okay, or I've estimated R just simply by looking at the data. Now I want to estimate a value for N0. In other words, the number of rats at T equals 0 months, right? So I can now use this equation 1. And I can do the number of rats at T equals 0, okay, is equal to N naught. Oh, sorry. What I'm trying to do here. What I'm trying to do here is work out N0. Okay, and that is N0 because if you think about that, at T is equal to 0, that's R to the power naught, which is equal to 1. Okay. So to do that, I can use any one of these values in this table. I am just going to let's just use the first value in the table, right? So I'm going to use an NT value of 4, and I'm going to use the number of rats at T equals 4, 784. Okay, so if I do NT equals 4 is equal to N naught R, and then to the power 4, I can rearrange this to get N naught. N naught is simply the ratio of N at T is equal to 4 divided by r to the 4, which of course is equal to, in this case, 784 divided by 1.5 to the power 4. Have I done that right? Oh, I think I've got, well, made a mistake here for a start. This was a 6. Sorry, folks. And this, which means that this is a 6. Okay, and I get an answer to the number of whole rats. You can't have half a rat. 151 rats. Okay, so at t equals 0, we start with a population of 151 rats. Okay, right, end of that question.